Hey there, APKL class. We are going to take a look at, it's calling it section 2.6b, and it's going to deal with finding derivatives of inverse trigonometric functions. So there are some formulas that are, they're kind of, a little bit long, and they seem to have a lot of pieces to them, but I'm going to break it down a little bit too, where you'd be able to maybe come up with these formulas through implicit differentiation if you didn't memorize them. But before we get to the derivatives piece, we're just going to kind of touch on and revisit what an inverse trig function really is. So just looking at this table, it says start the section by making a statement that none of the basic trig functions actually has an inverse. And what we're saying there is if you didn't restrict the domain of the original trig function, you wouldn't be able to find the inverse because they wouldn't be one-to-one functions. In other words, they're not necessarily strictly monotonic, meaning always increasing or always decreasing, or they would fail the horizontal line test, like the tangent and cotangent functions would fail the horizontal line test, even though they appear to be always increasing or decreasing, but because they repeat that shape, they wouldn't be passing that horizontal line test. Okay, so then in this table, it's just showing, and if you remember back from trigonometry, we did sketch the inverse sine, cosine, and tangent graphs just a little bit, but we did specifically concentrate on the range of the inverse functions, which would be the domain of the original function. We had to restrict the domain of the original function, so therefore that becomes the range of its inverse. And so with these restrictions, that just is going to create that one-to-one piece and allows us to get the inverse. Okay, and so these are just some of the graphs of the 6 inverse trig functions. You're not going to have to reproduce these graphs. It's just something that we can refer back to. So basically it's meaning like if we input a value into the inverse sign, or the arc sign means inverse sign. So an arc cosine means inverse cosine. That's just another notation. So you might see that ARC, which really means the same thing as our inverse notation, like that. They mean the same thing. But so when we input a 1 here, if we do inverse sine of 1, it's saying, well, what's the angle that we would be taking the sine of to get an output of 1? Well, it would be pi over 2, right? And we know that there's several angles that yield a sine value of 1, but in our restricted inverse function here, there's only one output for that, and that's what we need in order to actually have that inverse. We need that one-to-one relationship. Okay, so just a quick review of that, and then just doing a few of these problems where we're going to evaluate some inverse sine, inverse cosine, or arc sine, arc cosine values. I want to draw this out too, just in terms of a right triangle, or thinking of it in terms of trigonometry just a bit. So if I was looking for arc sine of -1/2, well, if we go back and look at this graph up here of arc sine, remember our values for our angles are going to be limited from -pi over 2 to +pi over 2. Okay, and we know that the input values that we can put into our inverse sine are from -1 to +1, right? So the input of -1/2 that's okay, because that's between -1 and +1. Now, but what it does mean is that, so if I'm thinking of sketching this out, and if this was my coordinate plane if I'm thinking of a unit circle there, I just want to be working in quadrant 1 and quadrant 4. So I'm going from -pi over 2, which would be down here at this negative y-axis, up to +pi over 2, which would be up here at this positive y-axis. So where am I going to draw this? If I was going to draw this out as a triangle, I would put, let me draw that just a little better so it's a little more to scale. So I would put a -1 here, and then I would put the 2 as the hypotenuse. And so I'm thinking to myself, okay, this would give me the opposite over hypotenuse value for the sine. Now, what angle would this have to be in here to have this, to have? And I say negative just because it's a negative y coordinate on this point on the terminal side would be coordinates -1, 2. And so I put that on there just to kind of show that's why we're saying negative. And that also tells us we're going to have a negative angle because we're rotating down like this. And so hopefully you remember that this means this would be a 30-degree angle. And I'm going to say pi over 6 because we want to do things in radians. And because it is rotating in a negative direction, the answer to that would be negative pi over 6 for that angle. Okay? So that angle right there is negative pi over 6, or negative 30 degrees, but negative pi over 6, okay, in radians. And we're always going to use radians in calc, all right? Okay, for this one, we're looking for the arc cosine, or the inverse cosine of 0. So, if we're looking at our inverse cosine graph right here, you're probably going to see, if we're inputting a 0, what are we outputting for that angle? And you can probably tell from the graph it should be pi over 2. But let's maybe draw this on a, in a unit circle, which is probably something we're more familiar with, or on the coordinate plane, maybe without drawing the actual circle there. But so if I'm inputting, 0, well, that means that, remember, as far as cosine is concerned, it's the x coordinate is the cosine value. So if we have an x coordinate of 0, that means that, I can't really draw a triangle, because you can't make a triangle with a side that has a length of 0. But it's one of those quadrantal angles, so it's going to be, right up here. So I'd have, my ordered pair would be 0, 1 there. Well, what angle falls, up here? Obviously, if we're drawing from here to here, that's my angle, that's going to be 90 degrees. Now, 90 degrees is pi over 2, which we can see from the graph of the inverse cosine here. We can see, like, if we input 0, yeah, you can see that output is at pi over 2 there. Okay, for arctangent of pi over 3, all right, so if we draw this one out. Now, remember arctan, if we look at that graph, that is, we've got input values that are basically, that are unlimited, but our outputs are going to be between negative pi over 2 and positive pi over 2. Okay, so with arctan, we have the input values can be anything from negative infinity to positive infinity, but our outputs are just going to be from positive 90 or positive pi over 2 to negative pi over 2. So we're kind of working on the right side of the coordinate plane, same as what we were over here with sine. Okay. So since it's positive, I'll put, and remember, tangent ratio was opposite over adjacent. So I want to have a triangle that has an opposite side of pi over 3 and an adjacent side of 1. And that's going to make this the long side, and this is the short side of my 30, 60, 90. And so this would have to be, 60 degrees, which, if you remember, that's going to be pi over 3 for that one. Okay. And this last one, this is basically just a calculator. You can't really draw this out, so you just type in inverse sine of 0.3, and you can type that in your calculator. It comes up to like 0.3047, I guess, is what we get there. Okay, next one. Okay, so in here it says to find the exact value of each. Draw a picture and to describe the situation. Okay, so what we're doing here is I'm going to do the same thing as before. I'm just going to draw a little coordinate plane. I'm going to draw my triangle with a, this is inverse tangent 3/4, which means the angle in question has an opposite side of 3 and an adjacent side of 4. So I'm going to draw something like that. So an opposite side of 3 and an adjacent side of 4. Okay, and that's representing, this angle right here in standard position. Now it's saying, well, hey, what's the sine of this angle? And so you don't actually have to figure out, how many degrees or radians this angle really is. What we're doing is we're just going to find the sine of it right away. So all that we need is the hypotenuse, because for sine we need the opposite, which we have is 3, but we need the hypotenuse, which we don't have, but we can easily find with the Pythagorean theorem, and we would see that that is 5. And so the sine of this angle that has the inverse tangent of 3/4, which we set that up in that way, would be 3/5, opposite over hypotenuse. So 3/5 would be the answer to that one. Okay, so in a similar way here, if we draw this out, and we've got a inverse sine of 1/3, that means we're going to have opposite is 1 and hypotenuse is 3. And so that's going to be, so if opposite is 1, let me redraw that so that it's more to scale. So opposite's 1 and hypotenuse is 3. And again, we'd have to do the Pythagorean theorem. 1 squared plus what squared equals 3 squared. Maybe 1 squared plus, and I'll just say x squared equals 3 squared. And so x squared would equal 8, and the square root of 8 would be 2 square roots of 2 if we put that in simplest radical form. And so the secant then, so secant, remember, is the reciprocal of cosine. So instead of adjacent over hypotenuse, it would be hypotenuse over adjacent, so it would be 3 over 2 root 2. 3, so hypotenuse over adjacent over 2 root 2. And I'm not going to be concerned with simplifying or rationalizing that. It's not really necessary. Okay, and in example 3 is similar idea, except they don't put necessarily numbers in there. It's kind of setting us up for these formulas that are coming next. So I'm going to just draw this one out, and that'll kind of lead us into finding how we can find the derivatives of these inverse functions using some implicit differentiation if we want to. Okay, so here I would draw out my right triangle again, and so just random. Now the thing is, it's saying, okay, we're talking about some angle that has a sine of x. Okay, so, well, what does that mean? Okay, so we've got some angle here, and if the sine is x, and that means that the opposite side to the hypotenuse ratio, okay, because remember x is like x over 1, so the opposite to hypotenuse would have to be a x and 1, like that. That way, if I'm taking the sine of some angle here, it would be x over 1. Now, if I want to do the cosine of that same angle, well, then I need to know this adjacent side. So if I'm going to do, the Pythagorean theorem to figure that out, remember, what I'd have to do is I'd have to take hypotenuse squared minus leg squared, and then take the square root of that, right? That's how I would work that backwards. I'd have to take the 1 squared minus the leg squared and take a square root. So what that leaves me with is 1 minus x squared under a root like that, and that would be my adjacent side there. So therefore, the cosine of this angle in question right here would be this expression over 1, which would just be square root of 1 minus x squared, like that. Okay, so, and for the last one, in a similar way, if I draw this one out, okay, this time we're looking at an arctan, so some angle that has a tangent of 3x, and remember your ratio for tangent is opposite over adjacent, so I'm going to call the opposite 3x and the adjacent 1, and then I can do my Pythagorean theorem, 1 squared plus 3x squared, and I have to take the square root of that. So 1 squared is 1 plus 3x squared, which is 9x squared, and so by the Pythagorean theorem this would just be 1 plus 9x squared for that side. And so if this is my angle in question here and I want to do the sine, I would take the opposite over the hypotenuse, and so that would be 3x over square root of 1 plus 9x squared. Okay, so I'm going to stop right now with the first part of these notes, and then we'll continue on in the next video and look into the derivatives of these.